The latest symbolism caught by the James Webb Space Telescope has left specialists in wonder, uncovering the universe in manners that were once thought to be outside our ability to understand. These pictures are not just enhancing how we understand the universe, but are also revealing bewildering peculiarities that suggest our current knowledge may not be satisfactory to fully comprehend the early arrangement of the universe. Settled hypotheses about the universe's beginnings are now facing challenges, pushing the scientific community to explore alternative theories regarding its origin. This brings up a vital question. How did the universe appear? And why are these pivotal revelations introducing hardships even for the most experienced specialists in space science? This requires a more careful examination of the true nature of the Big Bang and its evolving complexities. It may be time to reconsider the Big Bang theory itself, especially since its portrayal has often been distorted by the public. The Big Bang was not merely an explosion occurring within pre-existing space. It marked the actual birth of space itself, unfolding around 13.8 billion years ago, alongside matter and time. A central idea in modern cosmology is that of a singularity, a point where gravity becomes so extreme that the fabric of spacetime becomes infinite. Billions of years after the universe's origin, it has become evident that our vast home is part of a much larger framework. For scientists, this revelation has provided a crucial understanding of the universe's ongoing expansion, suggesting that space itself continues to grow, contrary to past theories that implied otherwise. It is believed that the first stars began illuminating the universe around 200 to 300 million years after the Big Bang, signaling the end of the so-called Dark Age when the first bright celestial bodies formed and began evolving into galaxies. However, the speed at which these galaxies developed remains a mystery. A notable moment occurred on July 22, when the James Webb Space Telescope revealed its first set of images, displaying several galaxies, some of which had already existed around 300 million years after the universe's creation. These galaxies, though younger than those observed today, were smaller and less massive, aligning with the scientific models of the time. In the early universe, the matter density was thought to be too low to create galaxies as large as those we observe now. This discovery began with the detection of 6 distinct redshifted bright spots, igniting one of the most significant cosmic mysteries in recent history. Despite their youth, these newly identified galaxies appeared nearly as large as our own Milky Way, sparking interest among researchers in Big Bang cosmology. When scientists examined a set of images taken by the telescope's near-infrared camera, they confirmed the presence of these distant galaxies. They used redshift data to determine that the light from these galaxies had traveled for over 1 billion years before reaching Earth. This suggested that these galaxies had formed between 570 and 700 million years after the Big Bang. This astonishing finding raises doubts about traditional cosmological assumptions, which had expected much smaller, less developed systems at this stage in the universe's timeline. Instead, the James Webb Telescope revealed galaxies nearly as massive as the Milky Way, contradicting these expectations. The stars within these galaxies had already accumulated masses exceeding 10 billion times that of the Sun, with one galaxy potentially surpassing even this limit. However, whether this speculation is entirely accurate is still under debate. Even if these findings are correct, the mass of the early universe would have been far greater than previously expected, significantly complicating the situation. The discovery of these galaxies presents a serious challenge to nearly all conventional cosmological theories. If even one of these galaxies is proven to be as massive as suggested, it would require a reassessment of our assumptions about the early structures of the universe. The matter density in the early universe would need to be significantly higher than initially believed. Another possible explanation is that these galaxies may have formed in ways that are completely unknown to us. These discoveries have raised questions that necessitate a reassessment of the Big Bang theory. Many space scientists have expressed frustration with these revelations, often voicing their concerns in scientific journals. Those who question the standard theories are frequently labeled as unconventional or extreme. However, even those who support the Big Bang theory are confronted with pressing issues. One of the primary questions is how, 13.8 billion years ago, something could have emerged from nothing. Did something truly arise from nothing, or was there an external catalyst for this event? Did the Big Bang happen randomly? Stephen Hawking famously suggested that the concept of time itself began with the Big Bang, meaning the event could not have been triggered by anything else or set off externally. Similar doubts surround the uniformity of radiation and matter across the universe. Regardless of where we look or at what distance we observe, there is a comparable distribution of structures, nebulae, and radiation throughout the cosmos. Modern researchers often explain this consistency with the theory of cosmic inflation. However, some experts have expanded on this idea, suggesting that the universe expanded in a more chaotic manner. According to this hypothesis, expansion occurred only in isolated regions, like bubbles, while other areas continued to expand indefinitely. This model raises the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own unique set of physical laws. Such a perspective suggests that our universe might not represent the entirety of existence but could instead be part of a far larger and more complex structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe has been proposed. This is just one of many cosmological theories. For example, a 1955 article in NASA's Hotshot magazine suggested that the universe might never have had a Big Bang and could have always existed, possibly for an infinite period. In this interpretation, the universe's growth would be absent, and the continuous formation of matter would give the illusion of slow development over time. One particularly fascinating theory emerging from quantum physics and string theory suggests that our universe might be a projection or simulation originating from a higher dimensional reality. While this may sound like science fiction, it connects with the concept of the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization, capable of using the energy of a galaxy, might theoretically create a perfect simulation of a universe. However, proving the validity of such a scenario remains a massive challenge. Exploring the depths of cosmology and the origins of the universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new imagery from the James Webb Space Telescope has reignited debates about the fundamental fabric of existence, forcing scientists to test established theories and reconsider foundational ideas about the universe. At the heart of this discussion lies the theory of the universe's origin, which serves as the cornerstone of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from a hot, dense state, rapidly expanding and resulting in the space-time and matter we observe today. However, the discovery of massive, mature galaxies just a few hundred million years after the Big Bang challenges traditional ideas about how quickly large cosmic structures could have formed. These findings suggest that the early universe had a much higher density of matter than previously thought, raising critical questions about how such large structures could have emerged so quickly. This forces cosmologists to rethink how galaxies, like those observed by the James Webb Space Telescope, could have formed so early in the universe's history. As researchers continue to examine data from the telescope, they are reevaluating the role of dark matter and dark energy in the formation of these early galaxies. The implications of these findings go beyond our current understanding of cosmic evolution, challenging the very structure of our cosmological models and urging us to ask deeper questions about the nature of the universe. Intricately structured and expansive cosmos we observe today. If these early massive galaxies truly existed so soon after the Big Bang, it suggests that our models of galaxy formation may need significant revision. Traditional theories indicate that galaxies formed gradually, with smaller structures merging over billions of years to create the grand spirals and ellipticals we see today. However, the presence of such massive galaxies in the early universe implies that either the process of galactic evolution was far more rapid than we currently understand, or that some unknown mechanism facilitated their accelerated growth. These findings challenge not only the standard model of cosmology but also our assumptions about the behavior of dark matter and dark energy. If dark matter played a critical role in galaxy formation, as many scientists believe, then the presence of such large structures so early in cosmic history raises new questions about its properties and distribution. Did dark matter behave differently in the early universe? Could there be an aspect of its nature that has remained undiscovered? Similarly, dark energy, which is thought to drive the universe's accelerating expansion, might have played a more dynamic role than previously thought. As scientists dig deeper into the implications of these discoveries, one thing becomes clear: the universe holds far more mysteries than we ever anticipated. The James Webb Space Telescope's observations have provided evidence that challenges some of the foundational principles of modern cosmology, compelling researchers to seek new explanations for how galaxies formed and evolved in the early universe. One major avenue of exploration is the role of primordial black holes. Some cosmologists propose that massive black holes could have formed much earlier than currently believed, potentially acting as gravitational anchors for the rapid assembly of galaxies. If true, this could explain how such massive structures emerged so quickly after the Big Bang. However, this idea remains highly speculative, as direct observational evidence for primordial black holes is still lacking. Another intriguing possibility is that new, unknown physics played a role in shaping the early universe. Perhaps some yet undiscovered particle or force influenced the formation of galaxies in a way that current models do not account for. Modifications to our understanding of dark matter, alternative gravity theories, or even entirely new paradigms of cosmic evolution could be required to reconcile these findings with existing frameworks. The revelations from the James Webb Space Telescope also have profound implications for our search for extraterrestrial life. If the conditions necessary for galaxy formation were different from what we previously thought, then it is possible that the environments where planets and life could arise may also differ. By studying the atmospheres of exoplanets with Webb's powerful instruments, astronomers hope to detect biosignatures, chemical signs of life, on distant worlds. Such discoveries could further challenge our understanding of life's place in the cosmos, pushing us to rethink the potential abundance and diversity of extraterrestrial life. At the same time, these findings highlight the importance of interdisciplinary collaboration in solving the universe's greatest mysteries. Cosmologists, astrophysicists, particle physicists, and even philosophers are coming together to reassess what we know about the nature of reality. The James Webb Space Telescope's observations are not just about galaxies. They are about our quest to understand the fundamental laws that govern existence itself. Looking ahead, future space telescopes and observatories will build upon Webb's discoveries, providing even more precise measurements and deeper insights into the cosmos. Upcoming missions, such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, will further investigate dark matter, dark energy, and the large-scale structure of the universe. These next-generation instruments will help determine whether the unexpected findings from Webb are anomalies or signs of a deeper, hidden truth about the universe's origins. Regardless of the final answers, one thing is certain. We are at the dawn of a new era in astronomy. The universe is proving to be far more dynamic, complex, and mysterious than we ever imagined. As new discoveries continue to emerge, we must be prepared to challenge our assumptions, revise our theories, and embrace the unknown. The cosmos is not just a collection of stars and galaxies. It is a vast and evolving puzzle, one that we are only beginning to understand. The journey of discovery is ongoing, and each new piece of data brings us closer to unraveling the ultimate mysteries of existence. The James Webb Space Telescope has opened a new window into the universe, and what lies beyond is more exciting than we ever dared to dream.